So I've worked out things for both the YY axis and the ZZ axis, and I've worked out the relative stiffnesses about both. Now the point is that if you're looking at the top of page 30, the relative Y stiffness is 0.94, the relative Z stiffness is about 0.98. Both of them are greater than 0.3, which is the criterion that the code uses to say, well, buckling is going to be more of a problem than just squashing material flat. The next thing you want to know are what the bending moments are. So the first thing you work out is the load, which you're actually given. 18 kilonewtons dead load and 25 kilonewtons live load, total 61.8. The next thing you work out is, because it might buckle about either axis, you work out the bending moment about both axes. It comes out at 2.47 about the YY and 1.23 about the ZZ. And you then work out the actual stresses. Sigma C naught D. C for compression, naught because it's parallel to the grain, so it's at 0 degrees to the grain, D for design. In other words, load over area, 2.06. Bending stress about the y-axis, bending moment over section modulus, 1.978. Bending moment about the z-axis, bending moment over section modulus, 2.06. So what we're saying is that at any point in this thing, I'm not quite sure how to draw this, there it is in plan. There will be, first of all, a stress over the whole area. There will also be a bending stress about here. And there will also be a bending stress about here. And somewhere, perhaps in this corner, where's the load put?
Bottom right, I think. Top.
The load's there. So really I should probably have drawn this the other way around to make it clear. If the load's there, the worst stress is going to be in that corner, because it will pick up the compressive stress on the whole column, it will pick up the bending stress about this axis, and it will pick up the bending stress about that axis. So somewhere there will be a point where all the stresses are compressive, and if it's going to fail at all, because they fail in compression, this is where it's going to fail. Right. You want to obviously compare these, which are the actual stresses that the load causes, with what the material can stand, the permissible stresses, which the Europeans call the strengths. Be very careful about this one.
The strength is permissible stress.
Strength is in effect permissible stress, yeah. So whenever you see a Eurocode referring to the strength, it's talking about the permissible stress. So first of all, what's the permissible stress in bending? It's the FMK, which is, that's the bending stress characteristic. Why characteristic is spelled for K, I don't know. Perhaps it is in German, I'm not sure. Does anybody speak German?
Yeah, I think it is.
I think it is spelled with a K, isn't it? So that's what you get in the laboratory if you tested a piece of timber. You then have to...
Does the M stand for material or...?
M stands for moment, K stands for
moment,
characteristic. It's, if you like, what they got off a laboratory specimen. Now, when you take it onto the site, of course, away from the laboratory, it gets subjected to damp, temperature, and all sorts of things. So this has to be modified, and you get FMD, and that stands for design. In other words, it's what you're going to use in the site situation. You get this by modifying FMK by, first of all, material safety factor, and then by this thing K mod, which allows for the damp and the temperature and all that jazz. Because basically, at the end of the day, this is the thing that you're going to compare with the actual bending stresses. Okay? So I've got FMD. Similar sort of argument applies to FCOD. The permissible design stress parallel to the grain is going to be the characteristic stress divided by gamma n and multiplied by something that allows for temperature and all that sort of jazz. Again, in the exam, I won't expect you to find these K mods. I will tell you what they are.
What's FC of OD stand for again? So
Compression at 0 degrees, in other words, parallel to the grain. Design value.
Would you ever put some sort of degree in there? Would you ever make it like to 10 degrees or something?
You can get it. For example, if we're building a roof truss, there's a roof truss,
that's
sits on a wall,
COD compression.
has got a member coming down like that.
But they're both forces.
Now then, if you analyse a roof truss, let's say something like that. This is in compression, isn't it? And this is in tension. So you've got a big compressive force coming down, and where it attaches to this, the force is coming in that direction, and the grain is running in that direction.
Would that be FC 90?
Well, it's FC whatever. It's not 90. It would be if it came in at right angles.
No?
45.
Oh.
Yeah, whatever that angle is.
But would that be in the exam? Like, would
No,
that?
that's too complicated. It's in the notes. It's mentioned in the notes. The thing you will come across is this one, which is also mentioned in the notes. And we're diverging a bit from columns now, so don't think that I'm talking about columns anymore. But let's say you had a beam, obviously with the grain running that way, sitting on a support. Then that force is at right angles to the grain, isn't it? So you would then be talking about FC90D. And that's what, you remember when we talked about bearing in beams and the crushing of beams where they sit on the support? That's why you use that. So it depends on what the angle is to the grain, but with columns, it's assumed that sensible people build their columns with the grain vertical. Okay.
Going back to resulting stresses, does the fact that the sigma mzd equals the 2.06, which is the same as the sigma c0d, does that just confirm that
It's just a coincidence.
Oh, is that just a coincidence?
Just a coincidence. It's not until you stuff them in the formula that you find out what the significance
Yeah, I was
is.
really
It's just a coincidence.
These two.
Right now, if you're dealing with a column,
That's the whole area.
we've got
Oh.
we've got these values, that one and that one. But when we come to apply them to the column, the first thing we've got to do is modify them because the column might buckle. So the next thing that they've got is a series of things they call the buckling factors, and this is what this huge piece of theory in the notes was all about, which you can forget and read up and impress your boss when you get a new job sort of thing, but in the meantime you can forget it. They first of all ask you to find out a coefficient called ky if you're bending it about the y-axis, or if it's buckling about the y-axis, and kz if it's buckling about the z-axis. Now, since we've got both of these situations happening at once, you've got to do each one. So down the bottom of page 30, there is ky and kz. And there is a formula in the notes which is quoted, 0.5 into that thing in the brackets. And they tell you that beta C is 0.2 for an order of timber column. So you have to work out ky and kz. Having got those, you can work out two coefficients called kcy and kcz. And then you can stick them in the design formulae, so 6.23 and 6.24. Now, which would be quoted for you in an exam paper. Now, if we look at the exam question, or the exam revision question, which is question 3.
Page that one. Or do you mean this?
In the exam
this is
revision.
the question we're doing now?
Yeah, if you turn back to the exam revision question, you'll see that basically what you're asked to do is what I've just shown you, and I've quoted all the formula you need to know.
Yeah.
I've quoted the formula that gives you lambda rel. I've quoted the formula that gives you ky and kcy, kz and kcz, and then I've quoted the formulae down the bottom in which you stuff all the stresses in to check whether it works. Now, do you want me to actually go through that on the next page? Because, I mean, I don't mind at all. let's zip through it and see how it lays out. I think so. On the next page, design 3, exam revision question 3. You're told that there's let's have a look at this one, because this is the biaxial bending bit, and I think most people have more trouble with the structures than they do with the design. So I'll draw it out in 3 dimensions for you, that's probably the best answer. We've got a column like that.
Which exam is
And coming into it, on one side, there's a beam like that.
Yeah, I've got 2 booklets.
Yeah.
On the other side, there's another beam.
I have 2. I took yours.
What page is it?
It's going.
And just to make life interesting, there is a third beam that comes in like that. Okay, so there's a column loaded from 3 directions. In plan, we're talking about that and that.
So is he now doing this?
And that. Now each of these, of course, will apply a load to the column. Come in. So the first thing I've done is I've worked out what these various loads are. And they come out at 6.75 there.
Sweet.
There. And
9.5.
And the reason I've drawn them like that on plan is I've assumed that they're actually connected on by using joist hangers, so that if I draw one of the details, if I draw that one, for example, what we're saying is you've got the column like that, and the beam is connected to it through some sort of hanger like that, so consequently the load is actually applied somewhere about there. And there's an example in the notes of what joist hangers look like, and if I put it in the exam paper, there will be a drawing of the joist hanger, so you'll be able to work it out for yourself.
The joist hanger, there's somewhere, where you sort of,
Oh,
you've got the
you got the overhang.
120, which is to do with the,
It's on page 17.
which is something like the platform area, you give us 60.
That's where the beam acts on.
Yeah, but
Yeah,
why,
you can basically assume that the weight of the beam comes down in the middle of the platform.
but you sort of, there, you do your 60 plus 30 and 30 either side.
Yeah.
And then in the questions it's about, you
Well-
assume a gap of 40 mils.
What the code says, it has a provision in the code that says that when you have a joist hanger, which looks like that, and has a platform like that, it's to do with crushing of the timber. When you sit the beam in it like that, with its grain running like that, then the contact surface is actually that, from there to there. Yeah. What the code says is that the timber beam will eventually, as it were, crush something like that, where that's the platform, and you can assume that because it crushes like that and has to bend these fibres, the effective area over which it's supported is from there to there. The effect of having to bend the fibres is to enhance the effect of this as though it was that wide. Now what the code also says is that that distance must not exceed 30, and that distance must not exceed 30. It might be even less. I mean, if you put it on, for example, like that, with just a small overhang, then you would have that. You have a little bit there, the width of the platform, and 30 there. But the point is, the code says you can't go more than 30. Okay, does that clear up that problem? Right, so where were we? Oh, we were on this funny thing, weren't we? So that's how I've got my various eccentricities. In addition, the problem also said that because this thing had a roof on it, there was also a load coming down from the roof anyway, in the middle of the column, of 36.75. Right. Now then, because these loads are unequal, even though these distances, that one and that one, even though those distances are equal because of the way it's built, because this load is bigger than this, there will be a bending moment in that direction about the z-axis, won't there? There will also be a bending moment due to this one about the y-axis. So there'll be biaxial bending. Now then, just to digress for a moment, what would happen if I had a beam that was loaded up like that, with say a big load there and a little load there? You'd only get bending about the z-axis, wouldn't you? Yeah, so just use your common sense, you know. Is it being bent about both axes? Is it being bent about one axis? Where does the bending moment come from?
So even if it was restrained like halfway along, you still only look at the z-axis? Like, not restrained stuff, how we were looking at.
You mean you're talking about restraint in the height?
Yeah, yeah.
No, you look at both.
But there's only bending about the z though, isn't there?
Yeah, but it still might buckle about the y, even though it's not being bent about the y. It's very unlikely.
Right.
But you have to check buckling about both axes, even though it's maybe only being...
Even if it wasn't restrained though, you'd just look at the z-axis?
Yeah, because it would be bound... Yeah, if it wasn't restrained in either direction, then it's quite obviously all you need to do is look at the z-axis, because it isn't going to fail the other way.
Yeah.
But if there's a sort of series of restraints, you've got to make sure that even though it's being bent about this axis, it might buckle about that one,
Yeah, yeah.
if there are sufficient restraints of the z-axis.
Yeah.
So you check about both axes, always. Right, so what have I got? I've got the axial load, I've got the I've got the actual compressive stress at 0 degrees to the grain, 3.12. I've got the bending moment, which is the difference of the loads times the eccentricity. So in my problem, this one is the 0.05, is 0.07 it is distance. I've got the bending stress about the z-axis, I've got the bending stress about the y-axis. That's the bit that says you get 6 marks for doing that. So basically, in this question, you can get 7 and 6, 13 marks without knowing anything about timber design at all. The first part of the question is theory of structures, which is, I think, extremely kind of me. There we are. Once we've got all these, we then go on to actually designing it. So we've got to timber bit. What's the design bending stress? It's 24, which is the characteristic stress, times K mod over gamma m. That's where the 14.77 comes from. Similar sort of argument for the compressive stress. If you notice on the previous page, these values are quoted for you. FMK and FCOK are quoted for you, 24 and 21. Check the buckling, build up the buckling factors about the y-axis and the z-axis. Again, the formula you use are all quoted in the internal question. stuff them into the equations 6.23 and 6.24 and see what happens. So at that stage, there are 12 and 4, 16 marks for slavishly putting numbers into formulae that you've already been given, which again you can do without actually understanding it, which is, it's very difficult to set an exam question which requires the student to understand what they're doing. If you do, they universally fail in my experience. So as I've got older and wiser, I tend to set exam questions where, provided you do what you're asked to do, you can't get it wrong. Having said that, there are innumerable ways you can get it wrong. The reason I do this, incidentally, is because the rules of the game have changed a little bit since when I was an undergraduate. When I was an undergraduate, if you did an exam question and you made a mistake, then of course it would affect everything past there. You got half marks for the rest until you made the next mistake, and then it went on to quarter marks. If you made the next mistake, it went on to eighth marks, by which time you were buggered. Now what we're supposed to do, because you're all clients, you're all paying enormous fees, is we're all supposed to encourage you to pass, even if you may be sort of totally illiterate and non-numerate. So we have to design exam questions which basically it's a bit like riding a bike, you know, you can't fall off. Now having said that, it's actually splendid for examiners, because under the old system what you had to do was you would start working out the student's thing until you got to the first mistake, and then you'd have to pursue his figures to see where they were leading, to see how many marks you could give him. And with 140 students, if they all made different mistakes, you ended up marking 140 different questions, which took hours and hours and hours and hours and hours. I try to set questions now where either you can do it all, I can show you, or alternatively you go so catastrophically wrong that I can go. Because the idea of pursuing 140 different variations of the truth doesn't appeal to me anymore. And anyway, you're paying. So there you are, that's biaxial bending. Now there is another possibility which is in a way going back to beams. How do you get a beam with compression in it?
I'm not.
So in a way we know off beams are going back to columns again. Okay. If you've got a long beam like that, it's loaded up, and you're designing it as a beam, you'd obviously be quite worried about lateral torsional buckling. Now this might get even worse. Now all we're really talking about is bending moments about one axis. It's a substantial bending moment because it's a beam, but it's only happening about one axis. But what happens if some kind person adds an extra problem to it by compressing the beam? Now that doesn't happen in beams, but where it does happen quite frequently is in a roof, where you have loads on the roof, and these loads are going to generate two things. They're going to generate, we can look at them like this, which is probably the easiest way to look at it. Each load we could look at as being a load at right angles to the beam and a load down the slope. So if I separate out these two, I'm going to have a series of loads like that, which are obviously going to cause bending about that axis, with the possibility then that I might have lateral torsional buckling problems. But in addition to that, I'm going to have a series of loads down the slope, which are actually, I've drawn them there, but they're actually, I suppose, in here. So I'm going to have a gradually increasing compression down the slope, which will be quite substantial. It's the sort of thing you get in, as soon as you put timbers into a roof and make them into an arch. Not merely do they bend, but the weight actually acts down the slope, which is why, incidentally, because the weight acts down the slope, of course, it's why you've got to make sure you tie the bottom together. That's why it does that. So the last one, question 4, is about a 3-pin arch, in which this phenomenon will occur of both bending and quite substantial compressions. But in a lot of the old-fashioned textbooks, they used to refer to it as a beam column, beam-column. What they meant by that was it partly behaved like a beam, it partly behaved like a column. It depends, its exact behaviour, the loads are easy, but the exact behaviour depends on how the loads are organised. For example, if, as in my example, the loads come in, these 7 kilonewton loads come in at intervals B, C and D. The purlins, it says, provide restraint against lateral buckling. What this means is that if I look down on it in plan, so this is a plan now, and what do I call it? A, B, C, D, E. A, B, C, D, E. This is where it sits on the wall. This is the ridge. So we're looking at A, where it sits on the wall, B, C, D, E, where it then leans against the other half. The loads are transmitted onto it, presumably, through purlins, which come in like that. And if it's going to buckle sideways like a column, then the most it can do, because don't forget, if it buckles sideways, it's going to buckle about that axis. So if it buckles sideways, because of the propping effect of these, the most it can do is buckle something like that. But when it comes to twisting, it's quite different, because there's your thing. If it wants to twist, and it's got something coming in from each side, I'll do it from your side. If this wants to twist, this joint isn't going to stop it from twisting. It can stop it from moving sideways, but it won't stop it from twisting. So, basically, this thing is restrained against buckling like that, but when it comes to checking twisting, which is lateral torsional buckling, it's only really properly restrained there and there. So the lateral torsional buckling length is something like that. So when you come to check the combined effects of bending and axial effects, lateral torsional buckling might be a problem because it's only restrained there and there. Straightforward Euler buckling probably won't be a problem because these are very short lengths. You can't really move sideways very, very efficiently. So, again, there's a degree of engineering judgment involved in designing one of these things. So let's have a look and see where it takes you. But read the question. Incidentally, I keep saying read the question. And I do mean read it, because in one of the pre-stress ones last year, I actually told people how to do it in the question, and did anybody take any note? No, did. And they all got it wrong, catastrophically wrong. I think the top mark was, the question was about 10. Out of 33-mark question, most people got 2 or 3. Anyway, let's read the question. Diagram shows a 3-pin arch. Does everybody know what a 3-pin arch is? It's that. The point being, have a little digression into first year statics, because I think it's worth it.